All right. So, so what I can do for now, for now, maybe I can turn it on and off, but that would take awfully long time. No, I really don't want to do that. So let's pull back the center one, and then starting tomorrow we'll have the both things. And I'm sorry, it's just technology is fantastic this way sometimes. We're assuming that it's going to work as well. See that something's happening. All right. So I'm sorry to try to look there. Hopefully everybody has today's lecture. This is what I'm going to use. Okay. There we go. So, stepping back a little bit, yesterday we talked about amino acids, and we started talking about the 20 amino acids. We of course talked about some very basic properties of amino acids and peptides, and that of course is the how the peptide bond is formed between two amino acids. And we mentioned, of course, is that we have always the alpha carbonyl and the alpha amino group. Both are involved in this, where a condensation reaction takes place, and the water is basically ejected as a byproduct. Okay, and that's our peptide bond. And we talked about the peptide itself. We mentioned that usually peptide bond is rigid, right? So this does not move. Those N and C, those nitrogen carbons, cannot twist around each other. However, those carbons, this alpha carbon and this alpha carbon, can easily rotate around it, and those are the phi and the psi angles we talked about. And one of the things we mentioned as well is that there is a directionality in any peptide where we have an amino terminal and a carboxyl terminal. And so in a peptide sequence, you assume always start from the amino to the carboxyl terminal. And of course, for each amino acid, we call a carboxyl side and an amino side. So for this amino acid here, there's a carboxyl side, which is the glycine, while on the amino side of glycine, there is tyrosine. Okay? So those are some of the basic concepts and terminology that we will be needing, and you will be needing if you take the next course, which is the biochemical methods, and any, of course, related courses. Here, of course, is the two peptide bonds between three amino acids, and here is the phi and the psi angle where you get the twisting. And today, actually, we're going to talk about this and the consequences of these twistings that we can form, the angles we can form, and hence folding of the protein. All right. We started talking about the 20 amino acids, that make up our peptides, our protein, actually every protein on Earth. Mentioned, of course, we have to memorize them, we have to memorize their structures, and their 1 and 3 letter codes. Now, so in an effort to understand amino acids and consequently understand the proteins that will be made up of those amino acids, we went ahead and started categorizing those amino acids based on their physical and chemical properties. And so today we're going to expand this concept and talk more about that, and talk more about the acid base, since there are amino acids, about the acid base properties. So we mentioned as a general category, we have neutral, non-polar, hydrophobic amino acids, neutral, and of course the R group of the amino acid, not the alpha carboxy or the alpha amino. The R group is what gives it its properties. So we're talking about the R groups here. The neutral, non-polar, hydrophobic amino acids, the R groups have no charge. They're generally hydrophobic. They don't like to be associated with water, and hence they tend to be buried inside the protein, inside the structure of the protein, and you'll see that a little bit. And then we have the neutral polar. In other words, there is polarity, and hence they can engage in some sort of interaction with the aqueous environment around them, and hence they'll be soluble. and those usually are on the outside of the protein because they will be interacting with the aqueous environment, namely the cytoplasm inside the cell, for example. All right, then we mentioned the acidic and the basic amino acids. Those are 5 amino acids, 2 acidic and 3 basic. Those are usually always charged under physiological pHs. Acidic will be always negatively charged under physiological pHs, and the basic always positively charged. Okay? Those are, in this case, are histidine, arginine, and lysine. Okay. Now, if we look a little bit closer and deeper into the R group, now we can try to understand that even further. If we were to subcategorize it, let's only talk about hydrophobic amino acids. Amino acids that really generally like to be inside the protein, away from water molecules. Those are the ones you see in front of you here. Alanine, valine, isoleucine, leucine, methionine, phenylalanine, tyrosine, and tryptophan. Now, what do you see in common between all these? They have aliphatic chain. Aliphatic chain means CH2, 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 something like that. Usually aliphatic chains from organic chemistry, they usually don't like to interact with water. Okay? Those are actually part of the lipids that we talked about yesterday. They like to aggregate away from water. And in the protein chemistry, the same thing happens. They like to aggregate away from protein, forcing the entire strand of that peptide to fold to where it will shield it inside, away from water. Okay? Okay. So basically they're aliphatic. Now we have some aromatic ones here. Those are the tryptophan, tyrosine, and phenylalanine. Tyrosine is just like phenylalanine. See, it's the same thing, except it has a hydroxyl group. Actually, some people call it hydroxyphenylalanine. So this hydroxyl group, however, has given tyrosine another advantage. Actually, it can, if it must be, if it's forced, if it's pushed, it can interact with water. Why? Because of that OH. There's a polarity between that oxygen and hydrogen, which will allow it to form some sort of hydrogen bonding with the water molecule, and hence it will be soluble. It will tolerate water. It prefers, because of this vast, large aromatic molecule or residue of it, like to avoid water, but it can be actually in contact with water. Methionine is aliphatic and it has a sulfur group. Actually, it's only 2 amino acids that have a sulfur group. Okay, that's our section. Now, the 5 charged amino acids, those are absolutely hydrophilic. They absolutely have to be on the surface. If they are buried inside a protein, they're usually in an aqueous environment inside the protein, microenvironment. But usually they're always outside, helping protein to, well, outside, what I mean by outside is they can interact with the aqueous environment. All right. Now, we have 2 categories. One, hydroxyl group amino acids, and that's serine and methionine. They both have hydroxyl group. They obviously can interact with water. They also have no problem being inside, it must be. And the carboxyamide group. And those 2 amino acids, asparagine and glutamine, or N and Q, those are derivatives of their acidic amino acid sisters, which is ascorbic acid and glutamic acid. Okay? And what they have here is what we call a carboxyamide group. Carboxylamide group. Okay? Those are the 2 amino acids that have carboxylamide group. And it's a polar group, so it can interact with water, and also it can be buried inside the protein. Now, cysteine, that's the other sulfur-containing protein in the family. That is actually unique because this SH, which is part of that R group of cysteine, can engage in what we call a disulfide bridge. So if you have 2 cysteines and the chain, they can fold the chain and they will be engaged in disulfide bridge. Okay? In this case, this would be called cysteine, I-N-E. Okay? 2 cysteines together make a cysteine. Okay? That's disulfide bridge here. So otherwise it's a cysteine. So cysteine is the only amino acid that can engage in disulfide bridge with another cysteine to make a cysteine, and hence actually forcing the peptide to bend. Okay? Remember, you can interrupt me at any time if you have questions. So just let me know. All right, glycine, the simplest of the amino acids, the R is simply an H group. Okay? That's a very small amino acid. That actually can fit almost anywhere. Can be outside, inside, can be internal, can be everywhere. Okay? That's a small amino acid. It comes in very complicated structures. Protein is our only amino acid, amino with an I, and the reason it's an amino acid because the alpha amino group is engaged with the R group. The R group here is bent and it makes a 5-member ring. All right? That makes it an amino acid. It's a protein. Protein is also an interesting amino acid. It helps in between different secondary structures, as we will see today, because proteins can fall into different units of structures, and protein can be in between them. All right, let's go to our first question. What's the amino acid that forms disulfide bridge? What's the only amino acid that can form disulfide bridge? Let me start the time. Now, another one. All right. When we form a peptide bond between two amino acids, what is the byproduct of this reaction, this condensation reaction? All right. 30 seconds. Actually, there is a timer here. Let's see the timer. All right. So now let's talk about the acid-base properties. Okay? It's an amino acid, it's an acid, and a base at the same time. Okay? So we're going to talk briefly about the titration curve of an amino acid, since it has two groups, one basic and one acidic. And then we are going to talk about what does that mean as far as the overall charge of the protein that contains those amino acids. Okay? And how we can figure out, generally speaking, if a protein is positively charged, neutral, or negatively charged, just from looking at the amino acid sequence and knowing the pKa. Okay? So, believe it or not, there's not much to memorize right now. It's just understanding. So you will be presented with a sequence and figure out whether it's positively charged, negatively charged, or. So let's look at the curve, first of all, the titration curve. So let's start from the way acidic. You have an acidic solution that has one amino acid, any amino acid, okay? And we're adding base. We're increasing the pH gradually. And so at the very beginning, when everything is acidic, the amino acid, and I want you to only focus on the alpha W and the alpha amino. Okay? We're not concerned about the R group. The R group will add a little complexity when we are talking about acidic and basic amino acids. But right now we're not interested in that. We're only interested in the two alpha groups. Okay? So at the acidic pH, everything is protonated. We know that from the organic chemistry as well. Everything is protonated when it's acidic. So the carboxyl group will be COOH, all right, has a proton, and the amino group will actually have that extra proton, will be positively charged. So this is the structure we have. Now we are increasing the pH. As we're increasing the pH, we are deprotonating. When we go from acidic to basic, we are deprotonating. We're taking proton away from whatever we are adding base to. So, as we're doing this, the first H will go out, the first proton will be from the carboxyl group. And so you can see here the concentration, this red here represents this red, the concentration of this species of amino acid is decreasing. It's decreasing as we're increasing the pH. So it's going down while the concentration of this species, where the carboxyl group is deprotonated, is increasing. You can see it's increasing. And we will reach here a midpoint, right here where the X is, where both concentrations of this and this are equal. And then we continue increasing the pH, and eventually we will have everything in this form, okay? Where the carboxyl group is completely deprotonated, completely, and of course the amino group is still protonated. This we call a Zwitter ionic form. A Zwitter ionic. Zwitter ionic means a molecule that has both positive and negative charge. And as you can see here, since the carboxyl group is deprotonated, it's negatively charged, and the amino group, of course, is positively charged. So it's Zwitter ion. It's Zwitter ion. Now, under physiological pH, This is always the case. Around 7.6, 7.3, that's our normal pH in the cell. Okay? Usually those two groups are always like this. Hence, we never say aspartic acid, we say aspartate, because it's always in this bitter ion form. Okay? Are we cool so far? Any questions? Now let's increase the pH. Let's increase the pH more. And now we are going from here and we're going to deprotonate the amino group. And so we're getting this species. And the same thing, the concentration of this will start reducing. And the concentration of this will start increasing. And of course, we're going to reach a midpoint where both species are at equilibrium. We continue increasing the pH. And we're going to get both groups deprotonated. Everything has no proton in it. So the carboxyl group will be negatively charged, and the amino group, of course, will be neutral. All right? So this is at the very basic spectrum, or the spectrum, the pH spectrum. All right? So this is a typical amino acid titration. Now, if we have an R here that's acidic, like aspartic acid, glutamic acid, then that group will be taken into consideration. But at least now we know if how both groups behave under acidic and basic conditions. Okay? Alright. Now, let's go back to Henderson-Hasselbalch equation. And let's talk about the case of what the protein would be experiencing under entry. Okay? Now, the pKa, which is a value where there's equilibrium between both protein and protein species. If the pH of the environment, that amino acid or that protein happened to be smaller than the pKa value, okay, that means acidic, that means everything is protonated. That means that group is protonated. Okay? That's a law that we need to know. Alright? If the pH is below the pKa, we will now flash the pKa values in loaded, which you don't need to memorize. But if the pH is lower than the pKa, then the groups, those groups, carboxyl group, amino groups, sulfide group will be protonated. And hence they will be looking like this, COOH. The amino group will look like this, NH3+. It will be positively charged. The hydroxyl group will look like this, OH. Okay? SH group will look the same. Now, on the other hand, if the pH is larger than the pKa, then, that's what's seen in the curve, it will be deprotonated. And hence, the carboxyl group will look like this, COO minus, NH2 will be neutral, and the OH will be O minus. SH will be S minus. Okay? That's what things will look like if the pH is higher than the pKa. So this is a visual way to visualize this, to see this. pKa, if the pH is right here, this is how these groups look like. And if the pH is higher, right here, then this is how the groups look like. Okay? Try just to visualize this. Acidic, because of the H, the proton, it's protonated, basic, it's deprotonated. Now you just need to rely on your organic chemistry knowledge and see what those groups look like, protonated and not protonated. And that is the only thing you need to know to figure out the protein charge. So, do we expect, aside, of course, of the amino group and the carboxyl group, do we expect any other pKa value for those amino acids? Are those other groups charged in any way? No, those are unfolded. They have no charge. So really, there's no pKa values. Because when those are in a protein engaged in a peptide bond, this will be engaged with the N of the other amino acid, and this will be engaged in the C with the other amino acid before it. And hence, there is no pKa value this R has to contribute. So they do not contribute to the charge of the protein at all. No pKa values. What about those? Well, the OH can be deprotonated, so it has a pKa value of 11. Very basic. It's very rare in the cell we can get to that pH. Otherwise, of course, it's going to be very basic and the cell will simply die. But it has a pKa value nevertheless about 11. Do you need to memorize this 11? No, you don't need to memorize it. But you need to know that this has an ionizable group. Tryptophan and phenylalanine are aromatic amino acids. Nothing exciting, no pKa. They will not contribute to the overall charge of that peptide or the protein they are. Aspartic acid and glutamic acid, absolutely. Absolutely. The pKa value is 5. That's below the pH, physiological pH of our cells. Right? So that means they're almost always ionized, unless they're in some sort of microenvironment. Something we've discussed there. But otherwise, they're almost always under physiological pHs are negatively charged. Basic amino acids. They all have pKa values, and they are actually mostly in the basic range, as we expect, and hence they are almost always positively charged. Histidine, however, look at histidine. Histidine has a pKa of 6, very close to our physiological pH. And this makes histidine the only amino acid that has a pKa very close to our physiological pH inside the cell. And hence, it can easily shift between protonation and non-protonation, just with a slight change of the pH. This is a very important feature histidine has. It's a very important feature many enzymes and proteins use in order to modify the structure or do some sort of active reaction. Then we will see actually in hemoglobin, which is an amazing protein, you will see how this is actually very important in allowing the hemoglobin to carry oxygen and nitrogen phosphate. It's absolutely. Okay, so histidine has a pKa value that's close to our own pH. All right, what about those? The hydroxy and the carboxylamide amino acids. Nothing exciting, no pKa values, they will not be ionizable, so they're usually neutral. They will. Say that again?
What type of question will be updated from the table?
Well, that's. So this is, for example, a sequence. We're going to give you a sequence like this, or longer than this. Of course, we use a reasonable length. So this is one code amino acid sequence. Right? So we assume here, this is the N terminal here, and this is the carboxyl terminal here, right? So we have the direction. So A, D, G, L, I, D, R, N, V, Y, K. We need to know what that means in terms of amino acids. Remember, we need to know the one-letter code for the amino acids. Okay? So if you look at this, and here the question, for example, what is the overall charge of this peptide at pH 7? Okay? That could be a question. All right, here's the table. And so, of course, we know from our rules that if the pKa is higher than the pH, then it's deprotonated. If it's lower, then it's deprotonated. Okay? So, first, we need to know what amino acids to consider in this peptide sequence. All right? For example, we have here D. What is D? Aspartic acid? Is D aspartic acid? D is aspartic acid. Aspartic acid is 4.1, and the pH is 7. So would it be protonated or deprotonated? It will be deprotonated, so it will be negatively charged, right? It will be right here. R stands for what? R for arginine. Arginine is a basic amino acid. It will look like this at pH 7. All right? So that's positively charged. What other amino acid should be considered here? What about Y? Y, what is Y? Tyrosine? That's tyrosine. Tyrosine is OH. pKa is, where is tyrosine? 10.9, way higher than it. It will be always protonated. It's going to be OH. So it's really neutral. It will not participate. Okay, what else? What about K? What is K? Lysine? Lysine. Lysine is a basic amino acid, and the physiological pH, the R group will be positively charged. Where is lysine? Here's lysine. 10, we're at 7, lower, so we protonate it will be. Okay, did we consider everything, or we still have two things to consider? Which ones? The alpha amino and the alpha carboxyl group. Alright, so here we have the alpha amino group that will be positively charged because the pH is 8, the pH is 7 and the pKa is 8, so it's protonated. And same thing with the carboxyl group, which will be, of course, it's right below here, so 3, I guess, and that will make it deprotonated. Okay, so now let's just do a simple math. Okay, the alpha groups, amino and carboxyl group, will cancel. That's 0. Those two will cancel. That will leave us with +1. So what's the overall charge of this peptide? +1. Would it be positively charged or negatively charged? Would be positively charged. Okay? Yes, yes. Two questions.
So I thought so the OH and the NH3+, why would that not be +2?
Okay, so we have a carboxyl group here. that will cancel. -1 plus 1 will be 0, right?
Yeah.
Okay, so this will leave
Like there's 4 on top and 2 on bottom.
1. So let me, 1, 2, 1, 2, 3. Okay, so no, there's 3. 1, 2, 3 that are charged. The OH is not charged. The OH is neutral, it's protonated, and the hydroxy group is protonated is neutral. Right? So that this, I added here because it has a pKa value here. Otherwise, I didn't have to. Yes, sir.
Do you mind explaining how you chose which amino acids?
Based on this table. I looked at the table and I did this, yeah. Yeah? Yes. One second. Yes. I went individually, of course, but usually if you have the table, just use the table as your guide. If it's not in the table, don't forget it. Make sense? Yes. I can't hear you, I'm sorry. Because of the table. Because of the table. So I looked at the table and I decided it doesn't belong. So that's why you have the table, there's nothing to memorize. Anybody else? Yes, ma'am. That's right. That's right. Well, and so again, I looked at the table and I looked at the amino acids in the table right here, and I chose yes. Absolutely. Okay. All right. Okay, is that cool? Is that simple enough? Conceptually? So all what we need to know is what's in the table. Right? And then the pH is higher or lower than the pKa. That's it. That is it. Okay, and then you will tell me the overall charge. Okay. Cool. So let's answer this question then. All right. A term, what is a term that describes a molecule that has both positive and negative charges together? What is that called? Yeah, that should be a simple question. All right. So moving along, now we know something about the amino acids, we know something about the behavior. Now let's gather all these behaviors of those 20 different amino acids and put them in a peptide and a protein, and let's see how they will influence now the protein function. Or rather, let's only talk about what the protein looks like, shape of the protein. Okay? It's a long strand of peptides. Now let's actually examine those individually. Now here's a trick question. Okay? Now we mentioned 20 amino acids. Those are the 20 amino acids that make life. Are there only 20 amino acids in nature? Is that possible? There are infinity number of amino acids in nature. Somehow those 20 were chosen for the life. Now we will notice now today that actually some of them can be modified chemically, and they will give us slightly different amino acids. And later in the semester we will notice also that we will deal with other amino acids altogether. Okay? But the 20, those are the building blocks of proteins. They are working forces in our cells. That means reactions, make structural modifications, etc. So let's talk about the structure of proteins. Protein, as you can imagine, is a strand of amino acids. Now those strands will not remain as one single strand. This will simply go through twists and turns to make structures, and those structures that the protein eventually end up at is really what makes the protein functional. If the protein is not in this three-dimensional structure, it will not function. It will be denatured. We call it denatured. Otherwise, we'll call it in its native structure. So folding of the protein to its native structure is absolutely important for its function. We will not have a functional protein if it doesn't fold. Sequence is, of course, number one, but then we have to make sure and ensure that this protein folds to its native structure. So, we will talk about the levels of structure. The primary structure is what we talked about so far, which is basically the description of the linear amino acid sequence. Just like the question before, I gave you a string of amino acids. That is the primary structure of any protein. It's basically reciting the amino acids composition of that protein. Okay? That's the primary structure. The primary structure then will start doing some twists, and we'll start having developed relationships between adjacent amino acids that are close to each other within that strand. And that makes that protein bend a little bit. okay, in order to form these. And those usually happen by weak bonds. Weak bonds, the one we discussed yesterday, hydrogen bonds namely, and then they can be stabilized later by van der Waals forces, ionic interactions, etc. But these adjacent relationships will give us what we call a secondary structure, which is what we're going to talk about today. All right? And we're going to talk generally about alpha helices and beta sheets. Okay? Those are the two very famous structures that we see in every protein structure. Now, once we have the secondary structures formed of the protein, then now far away amino acids will start interacting with each other within those secondary structures. And now we will have our tertiary structure, which usually, if we have a single-stranded protein, is our final main structure. If we have several separate strands of the protein that have to come together, then we call that a quaternary structure. Basically, different strands associated with each other. Again, they're mostly stabilized by weak bonds. And this is what I meant yesterday when I said weak bonds definitely rule our lives, because without them, those structures will not be stabilized. If those structures are not stabilized, proteins will lose their structure and hence their function. Okay? All right. So let's, this is a primary structure. This is a primary structure, of course, written in detail. And of course, again, we have the N terminal right here, and we have the carboxyl terminal right there. So there is some sort of now here is the primary structure of insulin. Now, there are many things to notice here. At least a couple of things to notice about insulin. First of all, insulin is made from two different peptide strands. Can you see that? This is one, chain B, and this is the other one, chain A. That's two chains. Each one is separate. Okay? Now, you'll notice here that we mentioned the three-letter code, but usually we mention the first letter code, right? But here in this case we said the three-letter word. Now, the other thing we'll notice is that we have disulfide bridges between cysteines. Notice that? Now, within chain A, we have two internal disulfide bridges. Of course, look, these are far away from each other. So for this bond to form, you can imagine that this strand will bend a little bit to get those cysteines together, closer together to form that, right? You can see that. And of course, then we have two disulfide bridges between the two chains. You can see here between cysteine 21 and cysteine 19, and between cysteine 7 and cysteine 7 of both chains. Okay? Those probably are involved in stabilizing that quaternary structure because we have two strands. Okay, make sense? Okay, so you can see now, this is that primary strand. That doesn't tell you anything of what this protein looks like. Okay, we're just simply mentioning the sequence and where the disulfide bridges are. All right, can we predict those things? We can, actually bioinformatically speaking, we can. If we have a sequence, we can have some sort of prediction based on our prior knowledge over the last 150 years of all these proteomics, protein analysis. We can look at the sequence and say, probably it will have a disulfide bridge here or there, but nothing is sure without actually doing that first. Okay. Now let's actually go deeper in the secondary structure, and let's talk about the alpha helix. Okay? First of all, very important point, secondary structures are always stabilized by two entities, the alpha amino and the alpha carboxyl glucoside. Okay? Those are the ones that are involved in the peptide bonds. The hydrogens are the ones that are responsible for any secondary structure stabilization. So hydrogen bond is the only one between those alpha carboxyl and alpha amino. So those three scientists are the ones that actually unraveled the idea of alpha helix, which was absolutely nothing in the 50s, early 50s. Then, and of course, he the one that published the and basically told us what alpha helix looked like. So, chemically speaking, alpha helix is basically a relationship between each amino acid that are about 4 residues apart. So, notice that this is amino acid 1, amino acid 2, and here are our peptide bonds, right? Between the two. Peptide bond, peptide bond. All right. Now, these oxygen and hydrogens will be involved. So amino acid number 1 will actually twist and get closer to amino acid number 4 here, number 5, and we will have a hydrogen bond between this nitrogen and this carbon, this oxygen. That will be a hydrogen bond. And then amino acid number 2 will twist that strand further and will get those two close to each other, and we'll have another hydrogen bond between those two alpha groups. And so on and so forth across the entire thing. We end up with a structure like this, twisted like this. You can see here those dotted lines are the hydrogen bonds, and that results from the twisting of the strand and getting those amino acids 1 and 5, 2 and 6 close to each other enough to form this hydrogen bond. And usually we represent it as a ribbon like this or as a cylinder. That's called alpha helix. The protein actually will form this kind of structure. Okay? What stabilizes alpha helix? Hydrogen bonds. Between what and what? Between the alpha hydroxy, the alpha carboxy and the alpha amino, the hydrogen. Okay, now these are some values of the rise about 5.4 angstrom. You don't have to worry about it. I just need you to know what is involved in making an alpha helix. Okay? Make sense? Any questions? That's an alpha helix. All right? Structure is a beta strand. Beta strand is basically the primary sequence that's stretched to the max. Simply take it like an ordered stretch. That's all it is. That's a beta strand. Now, when you stretch it as much as possible, what's going to happen is you're going to have an elongated strand that can loop. Okay? Like this. So this is a strand here. I'm having the arrow to represent that we're going from N to C. And you can see here this is looping. So this is a beta strand section, and this is a beta strand section. And the red arrows here, now they're red, they represent the beta strand part of this peptide, that stretched. Now we call this, because it's going this way and this way, we call those anti-parallel beta strands. Anti-parallel. They're not parallel, they're anti-parallel. Okay? And also, when you have two beta strands that are adjacent, in this case anti-parallel, then they will form the hydrogen bonds. Now, what other hydrogen bonds are involved? Which groups are they involved with? Which ones? The alpha amino and the alpha carboxy group, just like the alpha helix. Of course, except they're not that adjacent, they're actually farther apart, but because this loops, they become closer to each other, you have those hydrogen bonds formed. Make sense? Any questions? That is your beta strand. That's your anti-parallel beta strand. So does that mean we have a beta strand? Of course. So it can loop like this and then continue looping all the way. Now we have two parallel beta strands. Those also are stabilized by hydrogen bonds between the alpha carboxy and the alpha amino groups. Okay? Okay? Now that we have two strands together, they are actually promoted to a sheet. Now they become a beta sheet. So a beta sheet can have multiple strands. This can loop many times, and all those strands can be involved in hydrogen bonds, and you're going to have yourself a beta sheet. Okay? So a beta strand has no hydrogen bond. Two beta strands, or beta sheet, will start having hydrogen bonds between the amino and the carboxyl alpha groups of the amino acids. All right, here's what a sheet looks like usually. Notice that we have this fake imaginary gray between them just to represent that they are like a sheet. All right, and here is how we represent them as a very flat arrow. A sheet. You can see here, this is anti-parallel. This is also anti-parallel. And you can see they can actually, if you look at them straight, they can actually twist around each other, so they can make these really very elaborate structures. For example, they can make what we call a beta barrel. A barrel. You can see how beautifully knitted. These are all beta sheets that are drawn together in a beta strands that are drawn together in an anti-parallel fashion to make a pore, literally a hole that sits within the membrane. Okay, and make a hole inside it, allowing things to go in and out. Okay, so this is one of the ways we can allow the cell to communicate with the outside by having proteins like these, beta parallel. These are actually called porins because they make pores. Okay, so if you look at it in vertical way, you can see that it has actually holes that things can go through it. And it's a very... Now, if you look at this, no. The urea to stay in very small portions, hence blinding the amino acids towards each other. And what happened, he ended up having what we call a scrambled protein, non-functional. Why? Because really you have many different combinations of cysteine that can bind to each other. And so when you really eliminated the weak bonds, the forces of the weak bonds, cysteines just formed randomly. Okay? And that's about this one. So really, this is the idea here. Now I want to turn